But back to Dr. Gallison. His extraordinary academic explorations really began after high school when he graduated a year early and worked for a year in a physics laboratory at the École Polytechnique in Paris. A year later, he started as a sophomore at Harvard. His major in the history of science led to a PhD in how scientists draw conclusions to their experimental work. This was followed by a second doctorate in particle physics, also at Harvard. His second book, Image and Logic, explored the ways in which different branches of science speak to each other in boundary zones between them. Dr. Gallison was also the recipient of a Genius Grant from the MacArthur Foundation, as well as the Max Planck Prize. Like Albert Einstein himself, Dr. Gallison's interests span the spectrum, including the intersection of science and architecture, the arts, flight, and culture. So, without further ado, let's welcome Dr. Peter Gallison.
Thank you. Good evening, and thank you all for coming. Thank you for this very nice introduction. Tonight, I'd like to speak about time. The idea that we'll be talking about tonight is one of extraordinary simplicity, but it was an idea that came at the end of a long series of developments over many years by Einstein, where he had been struggling to understand the ways in which electricity and magnetism had to be understood if you were moving. If you were in a boxcar moving along tracks and you had no friction, it was going tremendously smoothly, you would see no effects with springs and bouncing balls and any experiment that you could do that used mechanics. But everybody thought that this was different if it involved light or electricity and magnetism. And Einstein came to believe that physics of electricity and magnetism also should show you no way to tell whether you're moving at a constant speed or at rest. This idea was embodied in what he and others came to call the principle of relativity. That he understood some years before 1905. Before 1905, he also had understood something else, that it should be the case that if we were in this room and I moved a flashlight at different speeds, that no matter how fast the flashlight was moving, the light coming out of it would still be traveling at that same speed, 186,000 miles per second. So Einstein had these two fundamental pieces of the puzzle in place, but he couldn't make them compatible. One day, he came to a friend of his and said, "I've cracked the problem. I know how to put this into a coherent theory. Time, simultaneity, that was the clue to breaking the impasse." Everything in this lecture is about that idea of how time coordination came to be seen as one of the most important problems of the early 20th century, and a model for how to make knowledge in science and even beyond. In fact, when Niels Bohr and Werner Heisenberg and Schrödinger were building up quantum mechanics in the 1920s, they took as their model Einstein's idea of coordinating clocks to define time. You see, Newton had thought that the world, the expanse of the universe, was something in which God intervened at every moment, at every place. In order for gravity to move or light to move, there was a constant recreation of the universe in some way. And he came to think of the universe as being what he sometimes called the sensorium of God. Time and space he thought of as having two aspects. An aspect that was available to us with our rulers and clocks, and then a more perfect realm that lay behind any experience that we could have. And in that realm, the purely equably flowing mathematical time and a pure form of space, an absolute time, was something that we could only approximate with our mere rulers and clocks. Well, Einstein, after thinking late in his life about what it was that Newton had done, he'd been writing this autobiography in a fairly dry manner, and he stopped in the middle of it and he said, "Newton, forgive me. Newton, verzeih mir. You did the best that any human being could possibly have done in your time." And Einstein was in a sense asking forgiveness for having overthrown those ideas of space and time through his special and general theory of relativity. And what he did was to abandon the idea of an absolute space and an absolute time that lay behind the appearances, and to replace it with the behavior of rulers and clocks. And the question came to be, what is simultaneity? Einstein couldn't anymore say with Newton when two things happen at the same time, just like that. He had to say, what are we going to do to tell that the two clocks are giving the same time? So he said, suppose a train comes into a station and pulls in front of me at 7 o'clock. What do I mean by that? I mean that the little hand of my watch is opposite the 7 at the time the train comes in front of me. Okay, that's pretty clear. But what do I mean if the train comes into a distant station? How do I know then that it's 7 o'clock there if I'm here? Well, he says we have to send a signal. Should we send the signal, say, at 7 o'clock, and when it arrives there, set that clock to 7 o'clock? No, that would be a terrible idea, he says, because if I sent a signal, say by telegraph, to these people over here, they'd get the signal long before those people over there, and so it would matter where I stood in coordinating my clocks. Well, that seemed like a terrible idea. So he said there must be a better way, and his better way was very simple. It was, I send my signal at 7 o'clock, I figure out how long it takes to get to that person, say by sending it round trip and dividing by 2. And then if I send it at 7 and it takes 1 second to get there, supposing that this room was 186,000 miles wide, then that person would set her clock by 7 o'clock plus 1 second. That's it. That was the idea that cracked the problem. So let me tell you about this idea. Einstein often wrote about the problems of relativity, and in particular about his ideas about space and time, as if they were questions, as he put it, that only a child would consider. Or sometimes, especially after the early 1930s, I think traumatized in part by the Nazification of Europe, he began to say, I think that the best place for a theoretical physicist would be in a lighthouse or a lightboat far out at sea and isolated from the troubles of the world. We know Einstein also through his later years at the Institute for Advanced Study, where he became the symbol of an abstracted, absent-minded professor with no real contact with anything more complicated than a bicycle. But in fact, Einstein was immensely learned in the technical arts. He studied them when he was at university in Switzerland. His father and uncle ran an electrotechnical firm. He himself took out numerous patents from which he collected royalties. He had patents on refrigerators and patents on electricity measuring devices. He had patents on new forms of compasses. He had many patents. And he was an expert, a court expert in trials that had to do with patents. So Einstein is in some ways our subject, but I also want to tell you some about his main competitor, if you will, in the struggle to come to a theory of relativity. And that's somebody who, unlike Einstein, who I think on Google will get you about 2.5 million hits, is much less well known among us today, although among mathematicians he's a hero, and that is Henri Poincare. Poincare, in his time, however, occupied a hugely important role. Poincare, when he was in his prime, was a leader of the establishment in philosophy and in literary arts. He headed up the Academy of Letters in Paris. He was simultaneously head of the Academy of Sciences. He was advisor to the government. He testified in ways that helped exculpate Dreyfus, a fact often forgotten. He was a person who was deeply patriotic and fundamentally internationalist, a person who wrote beautifully and whose works in philosophy became bestsellers the minute they entered the market in France and are still read avidly by philosophers of science today. He's somebody who helped create the field of chaos and of nonlinear dynamics. He helped introduce the mathematical domain of topology. He changed the way we understand differential equations. He altered much of our understanding of physics in several different domains. He was, in fact, a Renaissance man of his time, perhaps the last, and he was born in 1854 and died in 1913. He was a person whose views about time and space became fundamental not only for the discipline as a whole, but also for Einstein as well. What I'd like to do here is to talk about these two moments in which Einstein and Poincare come to think about time as being nothing other than the exchange of a signal, taking into account the time it takes to get from A to B. But to do that, we're going to have to take a somewhat circuitous route to understand why, in fact, asking questions about simultaneity in 1900 or 1905 was not just the domain of children or philosophers, but in fact a problem that spanned the spheres of physics, philosophy, and technology. In fact, became part of some of the most important technologies of the time. Interestingly enough, when Einstein introduces the idea of coordinating clocks, he does it with this metaphor of the train. When Poincare introduces it, he does so by saying, imagine two telegraphers trying to determine simultaneity across the ocean. Why would you need to do that? Because if you want to know where you are from north to south, that's easy. You look at where the North Star is. If it's right above, you're at the North Pole. If it's at the equator, you're at the equator. If it's in between, as it is seen from where we are, you can find that. But longitude, how far east and west you are, is a problem. If the Earth wasn't spinning, it would be no difficulty. You could just look up, check your star map, see what star's above you, and you'd be done. But the Earth is spinning on its axis. And since it's spinning, what's above us keeps changing. So if you want to know where you are from east to west, since the world is turning from east to west, you need to know what's above some fixed point, say Paris, and what's above you at the same time. And then you can tell how far apart you are from east to west. So finding simultaneity for map makers was a crucial problem. What I want to tell you about this evening is really that these metaphors are also more than metaphors. They're not just the abstractions that we read them. Now we read them as a kind of cute literary allusion. But at the time, Einstein was working at a patent office that was processing dozens and dozens of patents about how to send time along train tracks. And Poincare was head of the Bureau of Longitude in Paris, a prestigious position that was in charge of a worldwide effort to send time signals and determine simultaneity across the oceans of the world. Let's start with Poincare. Poincare was trained at the École Polytechnique, a school that was an engineering establishment from its beginning in the time of Napoleon, but also a place for the highest levels of mathematics and physics and chemistry, and has been ever since. Some parts of its history more emphasized the fundamental sciences, other parts engineering. But in 1870-71, France lost the Franco-Prussian War catastrophically to the Prussians. And this was blamed in large measure on the failure of the French scientific establishment. And certainly the scientific establishment in France took it to be its failure. And that was the exact moment when Poincare entered Polytechnique. And while he was there, he was a participant in a radical reformulation of the curriculum to equilibrate the engineering and the science, the pure physics and mathematics, so that the students were taught to move absolutely smoothly back and forth between, say, mining and running a ventilator shaft in a mine to get the methane out, and doing fundamental work with differential equations or mathematics. So Poincare, after he graduated, went on to the School of Mines and wrote this letter to his mother, among many. And one of the things that you see here is, that Poincare draws a map. Poincare maps everything. Whenever he has a problem, he maps it. One in the upper left-hand corner is very straightforward. This is a map of where they were traveling around looking for good places to mine. And in the lower part, you see a different kind of map. This is a map of the curve of his level of happiness at different times. Today, in a train, yesterday evening, and so on. He mapped and graphed the progress of his colds. He mapped and graphed almost everything you can imagine. In fact, when he was sent to be a mine inspector in eastern France, he had as his assignment being a kind of NTSB accident investigator, if you want to mix the present with the past. And he went down into mines, very dangerous work, immediately after explosions sometimes. As in this case, in 1879, 31 August, 6 p.m., the methane gas exploded in the mine, killing most of the miners there. A few staggered to the surface. And Poincare was among the people who went down on the rescue mission and the accident investigation that followed. He had to figure out what had happened. And by mapping the mine and mapping the detailed flow of air, he was able to track back two hypotheses about where this might have started, and eventually narrowed it to a little miner's lamp, a Davy lamp about this big, and found a dent in it, and deduced that this lamp, number 476, had been dented by a miner, that had allowed the flame inside, which is normally covered by a grill, to escape and ignite a methane leak that had developed in the mine. That was typical of Poincare. A crisis, a mapping solution, a rational decision about what had happened. In the domain, while he was doing this mining work, he was also continuing his pure mathematics, so from the grubbiest and most dangerous depths of the Puy de Magny, the mines of Magny, he began to struggle with the problem that the great mathematicians of Europe already knew were really difficult, like figuring out whether the planets would stay in their orbits or whether they'd fall into the sun. And he began from a fairly young age to begin to ask questions about this, to think about the equations, and he had a great idea. He thought, what if we didn't look at the whole orbit, but just imagined a big piece of paper and looked at the ways it was punched by the planet as it went around, and then just looked at the curve that was formed by the punch holes. Then we could maybe, by studying that, whether those punch holes are getting closer or farther apart, begin to figure out what was happening. Well, he was confident that he could solve this, show that the orbits were stable. He published a paper in which the title was Every Star Within Its Orbit. He was showing the stability and the continuity of the world in its largest sense. He believed in the stability and the continuity of the world he'd grown up in, the Third Republic France, a France of rationality and progressivism, in the sense of people could solve problems, they could pose them scientifically and rationally and come to solutions to them. And Poincare believed in this ideal. It was important for him. And the paper got published. He won the prize, Oscar II. The paper was distributed all over Europe. And then the copy editor sent to him, look, I'm correcting a few typos, and I found this one tiny little typo in the paper. Maybe you could just fix it. It's one case that you didn't explore. What if these two lines cross? And Poincare wrote back and said, it's not a little mistake. And they said, well, I'm sure you can fix it because we've already published it. The king's name's on the paper. The reputation of the world's greatest mathematicians have gone out. The thing has been distributed to the most famous mathematicians of Europe. And he said, no, it's not a small mistake. So the head of the prize committee sent out a sort of hit squad to go get back the copies from all the mathematicians. And so they would write to these mathematicians, for instance, could you have your maid please just have the copy downstairs? We just want to do a little erratum correction. No big deal. They got them all back. They pulped most of them. A few survived. Poincare rewrote the paper. In fact, he found that the planets will not stay within their limits, and that given enough time with even two planets and a little asteroid, the whole thing will become so complicated and unvisualizable as to become chaotic. And that was, in some sense, the beginning of chaos theory. But again, a crisis, a map, a rational solution. As he was working and becoming more famous in his various endeavors, in 1881, there was a decision to try to reanimate the goals of revolutionary France, which had been to rationalize weights and measures. They had, after all, done things like tried to make the week 10 days instead of 7 days because that was decimal and more rational, and it had the added virtue of eliminating Sunday and therefore thereby poking a finger in the eye of the church, which they liked too. So this was given up by Napoleon later in negotiations with the church. But the kilogram and the meter remained important parts of what they had done, but then not had much success outside of France. So in 1881, they gathered a convention of the meter, and delegates and plenipotentiaries from all the different countries gathered in Paris. A beautiful machine. This is one of my favorite machines in the world. It's called the Universal Comparator. And you put something on one side, and it will rule the length of that on another object. So you could take your very finely tuned meter stick on the left and then etch into other meter sticks on the right exactly 1 meter, very close to 1 meter. It's incredibly detailed work, but they had spent years developing the right alloy for this and the right shape. This is the original meter stick and the original kilogram. And when they all got done with this, they ceremoniously came to bury the meter. And this is the meter at the top here, in a triple locked vault with the kilogram K over here, surrounded by what were called les témoins, the witnesses, because they would witness with their bodies were anything untoward to happen to this chamber. So, for instance, were there to be a temperature to get to fire, smoke, something, they would be witnesses to this. So there was this sort of moment when the K and M the meters, and K the weight, were going to be, in a way, kind of sacralized as they became not just rod number 274, but K and M. But they couldn't finish the ceremony because they were missing a key, and they said to the Minister of the Interior, said, well, I'll get the key. And they said, no, we won't talk to you. You're the Minister of the Interior. This is not in France. And they had made this section of the building extraterritorial. So here you had the most precise objects ever made by humans that become the model and naturalized as K and M. They're buried, and then by being locked in this chamber, become the universal around in all respects. And it was in France, and yet international. In a way, that's what the French have wanted ever since. And the desire to form something which had a rational basis, in which France could take the lead, but in their national advance would depart from France and become something beyond France and universal. So Poincare became involved with some of these discussions, and there were attempts right away to distribute time and to standardize time in the way that they'd standardized the meter. Now, it's a little harder to just throw around clocks the same way you send. When you move a clock, there are all sorts of problems that arise. They've been trying to get the clocks right between New York, Washington on the one side and London on the other for 100 years and 200 years, 250 years, and it had never really worked. The temperature changes, the pitching of the boats, terrible problem. Anyway, in Paris, the observatory had the time measured from the stars, but then the question was, how would you distribute in Paris? And one idea was to send it through pneumatic tubes. Those of you old enough to remember department stores, or in France even pneumatic tubes, they would actually send little bills through these. Actually, you have one at the Science Museum here. Does that still exist in the children's section, where you can send a package by pneumatic tube? Anyway, they were going to send time through pneumatic tube by pulses of air that would shoot under the streets of Paris and then hit the mechanism on your clock and reset it. And this was the headquarters for that. And here is where you buy your clock. So you would buy your pneumatic clock here. What the Statue of Liberty is doing here, I cannot tell you. But the ladies and gentlemen here would be purchasing clocks for their estate homes or for public places or for so on. These became a symbol of modernity, that you could, for instance, see a clock like this, a pneumatic clock, and it was an object of enormous admiration. This idea of a coordinated clock being a technology to admire is something that's hard for us to imagine if you go by Penn Station in New York and you see the bull of a clock with its great accuracy, digital accuracy there. We don't even notice it. It's invisible to us. It's like seeing a personal computer, which wasn't invisible in 1983, and a rocket wasn't invisible in 1961, and a computer wasn't invisible in the 1950s. So things became, the coordinated clock became a symbol of modernity, and with the introduction of the clock and these networks of clocks underneath Paris, suddenly people went from not even having minute hands on many of their clocks to wondering about the delay that an arrondissement down here would have from the headquarters over here, because it would take 15 seconds or so for it to cross Paris. So they began to say, well, we want you engineers to fix our clock. We don't want to be 15 seconds behind the real time. And suddenly they began to think, wait a second, simultaneity is something that we want, something that needs to be understood as having a transit time in the signal. Now, it's much slower than the speed of electricity or the speed of light, but it was nonetheless a kind of awakening to what's both a practical idea, namely getting your clocks right, but also a symbolic idea, one that's associated with modernity and with the culture of being literally up to the minute. As the methods grew more sophisticated, the astronomers and longitude finders, for instance, wanted to send their time signals across the ocean on the underwater cables that were laid starting about the time of the Civil War, first to North America and then to South America, then all the way to Indochina, to Australia. It began to cover the world with these. In some ways, it was the biggest machine ever built. Millions of pounds of cables were covered with a sort of plasticized, like rubbery-like substance that was found in Malaysia and that compressed under the pressure of the water, covering the copper wires protected by steel bands. These were an amazing world-covering apparatus, a kind of World Wide Web avant la lettre. Anyway, when the signal arrived, if it was strong enough signal, you could run it on a seismograph-like machine and look at the signals that it produced. Well, as you see here, where the pulse arrived, it was quite clear, and then by knowing the rate that your ink is moving across the page, you could judge the difference of time between two pulses and make very accurate measurements. These are the telegraph keys that were used to send time signals in the early days. Now, all of this had another important aspect. The times of trains became very problematic. You see, before fast transport or fast signaling, it didn't really matter that every town and hamlet had its own time. But as you began to have trains that crossed large areas, especially large east-to-west areas crossing many times, there was a problem, because what time would you use? And so people began to use the time of the originating big city. If it ran from Chicago, it would be on Chicago time. If it ran from Boston, it would be on Boston time. If it ran from Paris across France and eastwards, it would run by Paris time. That's fine, but then you have a train crossing, one train track crossing another. Now you have two times, and if there's a local time, you have a third time. And so you can see that if you had 15 or 16 tracks crossing, you have a problem. So the train schedulers became some of the early advocates for getting rid of charts like this, which had dozens and dozens of times, and it became simply unbearable for them. Some people fantasized of a world time, like Fleming, who pictured enumerating the hours from A to Z minus 2 letters, which he took out, and then having the time be, if you imagined a spot in the center of the Earth going towards the center of the sun, and you had labeled the Earth from A to Z around it, minus those 2 letters, then whichever letter was crossing that imaginary line would become the world time. Other people wanted national times. There was a movement of astronomers that wanted a national time set in Washington, D.C. in the United States. Some people wanted time tied to Greenwich, some people to Paris. In fact, that led to one of the great battles of this whole period. You see, maps had to have a 0 of longitude, and therefore time, a 0 of time. When does the day start? And the British thought a really terrific place to put the 0 of time was London, a little observatory at Greenwich that they'd been very proud of for a very long time. And the French thought a terrific place would be Paris. So they entered in fact, they couldn't even agree where to meet in Europe, so they met at this less important country in Washington, D.C., and where they could find sort of a ground that was neither one nor the other. So they began to argue, and the British said, look here, 97% of the world's shipping and our clients use Greenwich-based maps. Why would you want to change that? The cost would be immense, the difficulties, the practical difficulties. Quite great. And the French representative, Janssen, said, clients? You speak to us of clients? This is a matter of philosophical importance, a matter of fundamental science and principle. We would not decide such things on the basis of clients. And this argument went back and forth furiously, and the French lost on just about every count at this conference. This was 1884. And one reason that they'd lost was that the American railroaders had decided that they wanted time zones. I mean, other people wanted time zones too, like meteorologists who had to agree on where a front was. You can't have 2 different times and get your weather map right. And there were birders who wanted to track the flocks of birds, and you can't track birds if you don't know which is the same flock as you're looking at different times. But the important role was really the train schedulers. And they got together and they had a vote based on how many miles of track you owned. So if you're a railroad magnate in New Haven and you own 2,000 miles of tracks, you get 2,000 votes. So literally the trains voted. And when they voted to divide up the system like this. This is November 18th, 1883, into roughly the system that we have today with Eastern Time, Central Time, Mountain Time, Pacific Time. And Canada, the United States, adopted this. So by the time that this conference convened in October 1884, the Americans and the Canadians and their countries dependent on them had begun to adopt this system based on Greenwich. So these times were based on Greenwich time. So the French suspected, rightly, that the British Empire had struck again and bought out the votes of the smaller countries and defeated reason and rationality, where equal votes from many different countries at an international forum should have taken precedence. This may remind you of some events more recently, but we won't go into that. So, after having been defeated in all these ways, the French said, look, we've lost about the beginning of the day, we've lost about the zero of longitude, we've lost, but every topic that we've raised at this conference, rationality has been defeated. Would you give a rational project one more chance? In the French Revolution, we divided the clock into 10 parts instead of 12, as this very reasonable French clock from the Revolution shows. And we would like permission from this world august body of scientists and statesmen to pursue the idea of the division of time, a measure of time that would be based on something more rational. So you didn't have this completely idiotic system of 365 and a quarter days in a year and 12 months of different length with weeks of 7 days and 24 hours in a day and 60 minutes in an hour and 60... I mean, it just doesn't make any sense. And so the world body said, do you mean we have to adopt this system? And the French said, no, 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 just let us take back the victory of being able to explore it and come back with a proposal. So the Americans and the British grumbled, but they said, okay, you can do this. They voted, they approved this. The French came back with this. Janssen came back and gave a furious speech in front of the Academy of Sciences about the dastardly deeds that he'd encountered among the Anglo-Saxons. And then he said, but we do have permission to investigate the decimalization of time. The measure of time should be corrected. The person who was in charge of this, the scientific end, was Poincare. So Poincare began writing papers about the measure of time before he was engaged in the problems of relativity. He was in charge of, the first thing he did was to convene people from all the different areas that might have to do with this, navigators, astronomers, railroad men, mathematicians, physicists. Everybody came together, and they began to explore these different possibilities. Meanwhile, he began to be more important in the Bureau of Longitudes, running these signals. They say they'd set up observatories all over the world. I don't want you to picture a beautiful bronze dome with people shuffling around in white coats. This is what you should picture, an 8x8 wooden shack with a guy with a pith helmet and a little instrument in there for sighting the stars, and then a telegraph cable going out to meet the incoming submarine cable coming in from Paris, for instance. They mapped South America. In fact, the Americans and the French were racing around South America, doing an experiment that was, covered the world. It would be 20,000 miles in length. These were immense projects. Remember, you're doing these precision measurements to a thousandth of a second, 6,000 miles from home by a gas lamp in an era that had no electricity, in the most dusty, unhygienic conditions you can possibly imagine. These guys were climbing up high into the Andes, and they'd say to the locals, to the Indians, can you see when you get up there? And the Indians said, sure, you can see when you get up there. And they got up there, couldn't see a thing. And they were trapped up for months in these freezing conditions. The tents blew down. The temperatures changed so fast, their measuring rods shrank and grew. And they finally asked the Indian, well, why did you say we could see up there? And they said, well, you asked, could we see? You could see the path to get up. But the French astronomers wanted to see the next valley, and they wanted to see the stars. They didn't want to see the stone in front of them. So they had a terrible problem up in the mountains doing these kind of maps and making these precision measurements. This is one that was done between Paris down through the observatory at Cadiz to Senegal, where the French were fighting a fierce war against the rebellion by the Senegalese against the French conquest. They set up their instruments in the forts and used the bunkers underneath them for climate control and stuck their sighting devices actually on the big guns which controlled the coal yards and literally shot the stars. This is another fort in Senegal. And again, they would be sending things back and forth. This was an expedition to Quito in Ecuador, and they were struggling to figure out the shape of the Earth by mapping longitude and latitude with the precision that their earlier expeditions in the time of the French Revolution had not been able to grasp. At the same time, Poincare was moving back and forth between these different branches of engineering, of understanding the conventions of the meter and thinking about what the convention for the measurement of time should be. And doing the mathematics of chaos, for instance. He's also very interested in fundamental questions of physics, including the very puzzling Michelson-Morley experiment. Michelson was the first American to win a Nobel Prize. He was working in the Navy. He was built this fantastically accurate device, which you see here, where you would take some light, split it into two parts, bounce it off mirrors, and have the light come back and interfere with itself. And if the waves came back such that a crest met a trough, you would get a dark spot, and if a crest met a crest, you get a light spot. So even the change of, if it took longer from one trip by even a half of a wavelength of light, you could see that happen. And he thought, I'll use this device to measure how fast we're moving through this world ether, this substance that's supposed to be the support for the waves of light. After all, every wave is supposed to be a wave in something, so everyone reasonably assumed it was a wave in the wave. Wave was a wave in something, and that something was called the ether. So he thought it'd be like if you were traveling on a flat car across the plains of the central part of the United States, and you wanted to know which way you were moving. You lift up your hand and figure out which way the wind feels like it's blowing, and you could tell which way you were moving. Well, this was a sort of wind measuring device for light. And he couldn't find anything, no results. He called it the greatest failure of his life. It's one thing to win a Nobel Prize for the greatest failure of your life, but still, he thought that he had not achieved what he wanted, namely figuring out our motion through the ether. So Poincare was terribly worried about that and other problems in physics as he was struggling to figure out how to solve this problem of how to change the measure of time. Measuring time is, as you can see from the clock, a little bit like figuring out how the best, most rational way is to divide the circle. Should you divide it into 12 parts, or 24 parts, or 36 parts? The way we have 360 degrees in a circle. Or should we divide it into 10 parts, or 400 parts? All of these things were up for grabs. So Poincare did what he always did. He sort of gathered everybody's ideas together and figured out, different ways to, if you divide it into 100 parts or 200 parts or 400 parts. And then he figured out what kind of multiplication would you have to do. If you ignore factors of 10, you just figure out how much real multiplication do you have to do to convert this new system into the old system, or to tell how many degrees you've gone if you go 1.5 times around. And he figured that there was only one measure, namely dividing it into 400 parts, that had single-digit multiplication for all the different things that you might have to do with measurements in a circle or time. So he said, obviously, the rational thing, divide the circle into 400 parts. Well, this idea went over like a lead balloon. The physicist said, over our dead bodies, will you get rid of, because that means changing the definition of a second, for instance. So it's not a second anymore, it's, say, a 100th of a minute instead of a 60th of a minute. So it was every instrument-making shop in France would have to shut down. Every experiment would have to be recalibrated. The only people that liked this idea were the astronomers who'd been using this system since the time of the Revolution. But the astronomers are not going to tell the train men and the electricians and everybody else what to do. So Poincare lost, but the lesson is very interesting. Poincare always saw things in terms of convenience. Convenience for us people. He's not interested in some super mind that doesn't care the difference between multiplying by 6 and multiplying by 17. 6 is easier to multiply for us than 16. And in every problem that he comes to, he asks, what's the simplest way of grasping the world? Not what did God choose at the beginning of time, but what's the simplest? And he believed that the simplest was something that wouldn't vary from you to me, that we would all agree objectively on what was simplest. So he didn't think that the laws of physics mimicked reality in some way. He thought that the laws of physics were chosen because they were the most convenient. But he did not, for that, think that they were arbitrary. He thought that simplicity was itself a fundamentally objective, shareable concept. So all during this period, these results from these cabling time people were coming back, and you can see, interestingly enough, in these charts that they sent back, that there's a column here, it's hard to read from the back, I know, time of transmission. And so they were very aware, even though this difference of time between, say, Brazil and Paris might be a very small amount of time, it was something they were measuring and worried about. And they knew that a correct definition of simultaneity would have to take it into account. Poincare then did the following. In January of 1898, right in the middle of these wars with trying to get the time right in the exchange of signals, he writes an article for a philosophical journal called the Review of Metaphysics and Morals. And he says that simultaneity cannot be understood in terms of absolute simultaneity. It can only be the exchange of an electrical signal by a telegraph, for instance, from one mapmaker to another mapmaker. There's no reference to physics. It's only about philosophy on the one side and technology on the other. But he says in the end, we probably won't need to make this correction because other corrections, for instance, the inaccuracy of the telegraph operators would probably be bigger than the inaccuracy of correcting for this. But in principle, he says, this must be part of what we do. Then he puts it aside, although he mentions it at a few philosophy conferences, until December of 1900 when he goes to a conference honoring the great physicist Lorentz. And Lorentz had figured out a way to fix up time in his equations by making a purely mathematical substitution that changed time into something a little bit different. Poincare suddenly realized that what Lorentz had done, which Lorentz thought was just a fiction, was actually just telegraphers sending signals back and forth, moving through the ether, and correcting for the errors that that ether would induce. In a sense, what you then see is, in 1898, Poincare joined geodesy and technology with philosophy and found that the same words, literally, simultaneity is nothing other than the exchange of electric signals, taking into account the time of transmission, could be said both of the technology and of the philosophy. In December of 1900, he realized that those same words cracked the problem of physics as well. Now I want to turn from the most famous Frenchman to the least famous German. Actually, by then he'd given up his German citizenship. And that's Albert Einstein. Einstein begins his thinking about these problems from a very different perspective. He writes a paper that's almost incomprehensible in its oddness. No footnotes, no mathematics to speak of, doesn't begin with any story about an experimental problem. He says there's an asymmetry in the explanations of the world that doesn't seem to be mimicked by the phenomena themselves. Even that was words that Poincare would never use. But he says, look, if you move a coil towards a magnet, the charges in the coil feel a force in the magnetic field, and so they spin around and light the light. If you move a magnet towards a coil, what we usually say is that the magnetic field gets stronger and the changing magnetic field makes an electric field, and that drags the charges around. So two different explanations. Both of them light up the light, but whether you're in one's frame of reference or the other doesn't seem to matter, says Einstein. He says the phenomena, magnet approaches coil, doesn't depend, is given just once, and yet we have two explanations for it. Later in life he said, why should I have shampoo and soap? I mean, one soap should be enough. He thought that two forms of mass, how hard it is to get something accelerated and how heavy something is, that's one too many. He thought two kinds of magnetism, electromagnetism and natural magnets, that's one too many. Maybe the natural magnets could be explained by just tiny little currents. Over and over again, Einstein does this. And he too says that to go any further, we have to correct this notion of coordinated time. So if you start with this idea of just saying at 3 o'clock I send out a signal, whenever you get it you call it 3, he says that's no good. For the same reason Poincare thinks it's no good. No, you have to take into account the time the signal goes. And Einstein, starting in 1902, first of all, he couldn't get his thesis through several times. Then he had terrible trouble getting a job even he couldn't get a job in high schools. He couldn't even get tutoring jobs. He was just having a terrible time. And finally, the patent office, through family connections, offered him a job, and he was elated. He went there. He loved his work. Across the street from the patent office is the main train station in Bern, and though it's a little hard to see in the picture, these are two of the famous coordinated clocks that were right there. They were hundreds of them going up all around Bern. It was considered so revolutionary that the newspapers, when they went up in the 1890s, proclaimed a revolution in time, because now coordinated clocks were everywhere. There'd be a master clock, one of these beautifully sculpted objects that received its time from the observatory and then sent it down the tracks. That one was from Bern. This one's from Berlin. And then it would go to different places, for instance, to this building on the Isle of Geneva. And as long as the trains they weren't time zones, you had one Paris time, one Geneva time, and one Bern time. After time unification, one clock, same building. Time coordination was a subject for the big fairs. For instance, at the International Exposition, there was a conference on coordinating time, and the head of the group that was working on this got up and made a speech and said, in an era where time is money, how could we dare have clocks that are incorrect? How could we use this antiquated system of the pneumatic tubes? What we need is a universally distributed electric time. That is the only way we will escape from the dreadful anarchism of time. And Einstein was in this world. This is, for instance, if you step out of Einstein's apartment and turn left to go to the patent office, the first thing you do is to walk under one of the most beautiful clocks in Bern, and there are many. In fact, in Bern, one of the things that's quite striking, if you go there, and you all should, is to see, you can see many of these steeples with different clocks on it at the same time. And you can imagine if you were trying to catch a train and there were 7 different times, it could make you unhappy. This is the patent office. Einstein worked over there. Had to show you that. And here's his desk. Here's one of the typical, in the federal building in Bern, was one of the first to get these new coordinated clocks, and they were very proud of them. There were 147 of them set up in the building, so everyone would know exactly what time it was. And on streets like the one next to Einstein's on the library, there was an electric clock, which sadly only the holes in the wall remain now, but it was one of these salient objects. In fact, they were all over Bern, and to go anywhere in the city was to walk by these very prominent, well-recognized symbols of modernity. Now, Einstein came to his work at the patent office on electrotechnical things. Quite honestly, his father and uncle were running a factory that produced electric motors, lighting apparatus, especially precision measuring devices for measurement, like those little meters on the back of your house that measure how much electricity you've used. And they advertised that these were perfectly good for regulating things. They could also be used as electric clocks. They had patents out in them. Einstein visited these factories. So he came, even before he went to the patent office, he knew quite a lot about these patents. Here's a typical one where you see the groups of coordinated clocks here. And Einstein was in the section of the patent office where they saw these. In fact, starting in 1902, right after the invention of radio, people started worrying about sending time by radio waves. And in fact, there were big articles in 1904 and 1905 about this new technology of sending time by radio. So Einstein was, in Bern, the center point of the coordinated clock industry for Europe, in fact, for the world. And he was at the patent office where all these patents converged, in the section of the patent office where these patents converged. He's also meeting with his friends, like Poincare. He's very interested in philosophy. And they meet, only not in the Academy of Arts and Letters in Paris, but in Einstein's apartment with his 2 or 3 buddies, and they called themselves the Olympia Academy. And if they had enough money for wine and cheese, they got some wine and cheese, and they read Hume and parts of Kant and Pearson. And perhaps they spent, according to the recollection of some of its members, the most time studying the philosophy of Poincare. One of the great mysteries has always been, what did Einstein know about Poincaré's work on coordinated clocks that he had published in 1898. That was published in French, naturally. Einstein read French badly and unhappily. But the book that they did read was Science and Hypothesis. But in the German edition of Science and Hypothesis, the translator, crummy translator, but he's a translator of the French edition, actually took the entire passage about coordinated clocks that was and put it into an enormous on-the-page footnote. So I think it's certain that Einstein saw that piece of Poincaré's work, although it's much less certain and not even clear what it would mean that if he read Poincaré's later physics work on the subject. So one day, around this time, in middle of 1905, mid-May 1905, Einstein moved out of the center of Bern, that beautiful street, the Kammgasse, where the coordinated clocks were, into a part of town where there were no coordinated clocks. And he took a walk that day, the next day, with his friend Michel Bessot. And they were walking up in the hills, and Einstein stopped and said, "Michel, I know how to crack the problem of relativity. The answer is time, coordinated time. Suppose we want to coordinate that clock tower down in Muri," and he was pointing to this clock tower right there, that clock, there's only one clock tower in Muri, and that's the only clock on it, and some clock in Bern, I don't know which. Muri is the aristocratic annex of Bern. So we can figure exactly where they were. There's only one place where you can see these things, and that's right up on that hill. And he said, suppose we want to coordinate clocks. Well, we have to send a signal by light or by from one place to the other, taking into account the time of transmission. And then he said, with this, I can put together these two principles that I had before, the principle of relativity and the independence of motion of the light source. So in the midst of all of these patents, all of these discussions about coordinating clocks, philosophical discussions about the conventionality, about how we decide how to measure time and what time and simultaneity really are, and physics problems about how to put these principles together, suddenly it became clear to Einstein, as it had to Poincaré before him, that the answer was in synchronizing the clocks. Only for Poincaré, synchronizing the clocks had come late in the argument and a way of interpreting a move that Lorentz had made and deep in the mathematics of his theory. For Einstein, it starts as the beginning point of his whole argument. So they play different roles in the two theories. Poincaré, meanwhile, has not lost interest in this subject at all and has begun building. He helps rescue the Eiffel Tower from destruction after the fair that it was built for. It was going to be torn down by the city of Paris. And Poincaré was asked by military, can you help us rescue this? We want this as a radio tower. They were sending signals to their troops in North Africa so that they could command them what to do by radio. And these horse-drawn carts would be galloping along in North Africa with a radio set in the back and the guy trying to tune it and getting signals from the Eiffel Tower. So Poincaré thought, I'll do this, and the way I'll save this tower is I'll make it into a giant radio station that sends time out all over the world. So he designed this system with others. These are the elements of it. And this is the radio station at the bottom of the Eiffel Tower here. And Poincaré was up one day talking with the engineers, building these sets, testing them, testing their range. The next day at a conference saying, to understand the relationship of simultaneity, you have to exchange time signals. To be altogether modern, we should think about this as a radio wave. Back to a philosophy conference. So from the technology to the philosophy to the physics, back and forth in very quick oscillation. It's not as if the story of time begins in physics and only then becomes technology, or is really about technology and only then becomes physics. It's really a complicated oscillation back and forth, a kind of opalescence in which all of the different scales are present at the same time. So now this idea of that Einstein starts his paper where he says how we exchange time signals, and he says, this is a bad system to just send the signal and not take into account the time of transit. Now doesn't seem like just a straw man. It seems Einstein is describing the system that governed all the railways. All the clocks and coordinated clocks that he was looking at were all of this kind, and that what he was making was a principled correction to that. And in many ways, that's the way he was trained. That's what he wanted to do at the patent office. That's what he loved about his work. The only teacher or master that he ever really listened to was Friedrich Haller, the head of the patent office. He hated his teachers in college. He disdained Minkowski, one of the great mathematicians. Minkowski, when he heard that Einstein had this great idea about relativity, said, "That lazy dog did that?" He cut lectures. He paid no attention. He fought with his thesis advisor, Weber, whom he considered to be an idiot. He wrote letters to famous physicists at the time, making fun of them for what they said. I mean, it was the worst job-getting strategy ever recorded. And but in Einstein's case, it seems to have worked out. He was taught by Haller, whom he did listen to, that you have to understand technical diagrams. You have to really understand how to extract the principle of the thing, and to never give the author credit for knowing what he's doing. That Einstein thought was the greatest thing he'd ever heard. He was not inclined to give anybody credit for anything. So, whereas Poincare was co-authoring papers with his professors at age 18, and joined the faculty of the École Polytechnique very quickly and easily, was a member of the establishment, cousin of the President of the Republic, Einstein was blasting his way through, making enemies right and left. And it's interesting that it's now, if you look at the physics textbooks, you often see that the people who think about the problem of coordinating clocks in a kind of machinic form are the people who have had real experience with engineers, like John Wheeler, whose textbook has one of the most vivid of those references. But now, of course, this isn't, but it wasn't then an abstraction, it's not now. But we can see the three levels at which this story of how to coordinate time takes place. In some ways, Lorentz, the great Dutch physicist, had simply made a fictional substitution. Poincare had given that fictional change of variables where it's, like you have an equation where 2x appears everywhere and you simply redefine it, y is equal to 2x, and make things look simpler. That's what essentially Lorentz was doing. Poincare could explain this and give it physical meaning by thinking of telegraphers exchanging signal in an ether, and Einstein said, there is no ether. I don't care about the ether. And we will simply coordinate our clocks by the exchange of light signals, and then we will be able to reconcile these principles at the center of our theory. That theory now has gone back into circulation in the technological realm in many, many domains. One of the most important, of course, is the GPS system, which are beautifully synchronized satellites hovering high above the Earth and exchanging signals with your, rent-a-car, never get lost Hertz GPS receiver, and sending bombs down to blow up buildings in Iraq, and serving surveyors and geologists to figure out, using computer corrections, the differences of motion of even fractions of a millimeter. It's an extraordinary technology, and it depends fundamentally on not only Einstein's special theory, but on his general theory of how to coordinate clocks. In fact, when the first of these satellites went up, I can't resist telling you this, the engineers said to the physicists, we're not putting in Einstein's theory of relativity into this satellite. And the physicist said, you have to, or it will go bad in 15 minutes. And so they compromised. And they put in the correction device, but had it only to be turned on by ground control, so that the satellites would run, and then if they started going out of sync, you could turn them on. And the engineers said, don't worry, we're never going to have to turn them on. So they went up, and happily enough for Einstein, 15 minutes later they were way out of sync. And the engineers said, okay, I guess relativity does have something to do with engineering, something that Poincare and Einstein, I suspect, could have told them a while back. I'll just end by telling you one last story, and that is Einstein and Poincare each have one of the largest scientific correspondences in the history of the world. They corresponded with everybody, from public to heads of state, all of the major scientists. They're extraordinary archives, riches of which some will be displayed here, actually, in the show, starting in not too many days. They never exchanged a single postcard. They never spoke to each other, or rather they spoke to each other once in a conversation that was overheard shortly before Poincaré's death at one of the great Solvay conferences. And Einstein was presenting some of his work. There was a session on this. Einstein did 3 things in 1905. He showed that atoms really should be taken seriously physically, theory of relativity, and a third paper where he started quantum physics in a fundamental way. It was a good year. And in fact, that was just one issue in the year. Then there's a 4th paper, which is E equals mc squared, which also had some impact. And so, but in that light quantum paper, he violated everyone's understanding about what light was. And Poincaré was head of the session at which Einstein was speaking. So Einstein got up, gave a talk about this quantum and how light was like a particle, but also it was like a wave. And Poincaré, who believed in the rationality of mechanics really fundamentally. In fact, he'd been asked to come back to Polytechnique once and speak to the illustrious graduates from it. And he said, you are the generals, you are the politicians, you are the heads of industry, you are the heads of science, you are running the world in a way over empire and in the empire of science as well. What do we have in common? What do all of us have in common? And he said, what we have in common is a respect for mechanics. Mechanics, the rational understanding of the world, is at our core. It's the factory stamp of École Polytechnique. Okay, cut back to 1913. He comes to this conference. Einstein gives this talk in which he says, it's a particle, but it's not. Well, light's a particle, but it's not a particle. It's a wave, but it's not a wave. And Poincaré says, this is a contradiction. And from a contradiction, everything follows. There is no science here. This is a violation of our very understanding of what science could be. So that wasn't a good start to their a beautiful relationship. But they went and they spoke to each other, and de Broglie, one of the de Broglie physicists, overheard them. And Poincaré had one question for Einstein. He said, what mechanics are you using? I mean, Poincaré was willing to say we need new mechanics. Look, this is the person who introduced chaos theory, who said that the planets would not stay in their orbits. This is somebody who's willing to change our ideas of space and time in many ways. And he called it the new mechanics because it had a rational foundation and so on. But here was this idea of the quantum, and he said, what mechanics? What's the equations that govern this? What's the equation that tells how things evolve from moment to moment? The differential equations that tell us how the world changes in a rational, graspable way. And Einstein says, no mechanics. And I think they couldn't speak anymore. I mean, that was the end of any possible discussion. So they went back home, and Einstein wrote to one of his friends and said, I met Lorentz. I love this man. He understands what I'm trying to do. He grasps physics in its totality. And he says, and I met Poincaré. Poincaré understood nothing. It was such a disappointment. Poincaré went home after this experience with young Einstein. He's now in extreme pain. He's not doing well from the disease that's killing him. And he writes a letter to the ETH, the Eidgenössische Technische Hochschule, the Polytechnic in Zurich, where Einstein had been, and for a job for Einstein. And he says, this is one of the most extraordinary young scientists ever. Many of his ideas will no doubt turn out to be false, but if even one of them turns out to be correct, it will change the world. And I think that it may even have had an effect on what Poincaré went on to do after that. He published a paper very much unlike the ones he'd done before. He asked permission from the journal editors to speak more speculatively, to sort of take a guess at how the world might go. And some of that paper still fascinates mathematicians to this day. So I guess if we wanted to conclude, we might say this, that if we look at the time of Einstein and Poincaré, and we've taken an old expression of the alchemists who thought that the heavens and the things here on earth were connected. They said, if we look up, we see down. If we look to the stars, we see what's in the laboratory. In a way, if we look to metaphysics and the abstract aspects of physics, we see down to train tracks and telegraphers and radio senders on the Eiffel Tower. And if we look down to these technologies, to the nitty-gritty bits of experiment and so on, we see up to these abstractions that Einstein and Poincare introduced and that transformed not only our understanding of space and time, but the very model of how to do science. Thank you.
Gallison will be repeating your questions, so if you can make them as brief as possible and easy for him to repeat, that'd be great.
Yes.
Why is Poincare not a household word?
So the question is, why is Poincare not a household word, which he was back in 1905? Well, see, Poincare, in 1905, I think as a reasonable person, you could have easily said, Poincaré's equations are like Einstein's equations. Many physicists did say this. Basically, he uses the ether. Einstein says there's no ether. Both of them work. Poincaré, if you said, why do you keep the ether if you don't think it really has any measurable properties? He knew it didn't have any measurable properties. He was completely up to date on the physics. But he thought it was an aid to intuition, and there's no reason that we should give up an aid to intuition. I think for Poincaré, it would be like saying, to a carpenter, it was as if you said to a carpenter, can you build a house without a hammer? Well, the carpenter might say, I could, but why would I build a house without a hammer? And Poincare, I think, would have said, why would I try to build physics without the ether when it's such an aid to intuition? And Einstein would have said, look, the physics equations should reflect the phenomena of the world. There's no difference between moving the coil or moving the magnet, and the equations should show that same symmetry. Einstein wanted a kind of match between the phenomena of the world and the equations. And Poincare didn't care about that matching aspect. He wanted it to give you the correct predictions for experiment, but he didn't care if it matched the world. He never would ask the question, what did God understand about the world? Physics was for us people, who have our own human intuitions. And he was willing to save things for that. But Poincare, as physics developed, the Poincare point of view lost out. And it becomes extremely convenient for the conduct of physics, as it becomes more complicated, to ignore this idea of an ether which corresponds to nothing measurable. And as you go to general relativity, the way Einstein formulated special relativity, and then as it gets mathematized later by people like Minkowski, and then Einstein takes over that and brings it into the ideas of space-time, the older ideas and intuitions afforded by the ether are even more cumbersome. So in a way, physics didn't go the way Poincare thought it would. But his contributions to understanding the world, his rigorous sort of French Third Republic rationalism, his hopeful rationalism, is a fascinating counterpoint to the story of Einstein. And really, it's a moment when you can see two people of enormous insight, both of them in a way modernists of different kinds, not a modernist and a knuckle-scraping conservative, but two people who both wanted to change the world, but to do so in very different ways. And in a way, Poincare belonged to that older era, an era that didn't find its echo in either the science or the culture of the years that followed. Yes?
The relativity principle, what is it that's relative and what is it relative to?
Well, if you want to make a measurement, you're always in some frame of reference. That is to say, we imagine some grid of rulers and clocks that we lay out. So you might be, as I mentioned, when Galileo imagined this, he pictured boats smoothly sailing across the Mediterranean, and you, physicist, in your cabin without windows, and you do experiments with mechanics, and you have goldfish in a bowl, and it drops water, and you bounce a ball, and you do these, and nothing you can do tells you that you're in motion. And so, in that sense, it's relativity because the physical phenomena is valid in one frame as in another. The contrast is to some sort of absolute space, and there is no absolute frame of reference that determines the way physics really is. That physics is just as physics of mechanics is just as good at crossing the Mediterranean north to south as east to west. And what Einstein did was to generalize that to phenomena that included light and electricity and magnetism as well. Now, in the theory of relativity, certain things are relative to the frame of reference. For instance, if I clap clap twice separated by a second, and you're moving towards me, you will see that taking a different amount of time than a second. Not a second, but perhaps longer. And other things, however, there is a new kind of absolute, if you will. The speed of light is the same in every frame of reference. The fundamental equations of physics are the same in every frame of reference. So in a way, you trade certain things become relative where before they had been absolute, and other things that were relative become absolute. Yeah, does that answer your question?
So that relativity principle is the same as Galileo's relativity principle.
The principle of relativity in Einstein of 1905 is the same as the principle in Galileo, except that it now includes phenomena that Galileo would not have included, like electricity and magnetism and light. Yes?
When you talked about Einstein, before he became famous, would write letters to physicists and so forth, saying, I read what you talked about and I think you were wrong. Gives the impression that Einstein, early in life, really thought himself to be very smart, smarter than most people. What do you think in his early life helped him to gather this idea that he was a little smarter than most people were?
I think that Einstein, it wasn't so much that he thought he was smarter than other people, but he was very suspicious of authority. And one of the things that he wrote after he had this exchange with Drude, one of the senior electron physicists in 1902, 1903, and he had an exchange with Drude, and he had sent criticisms to Drude of Drude's paper, just laid them out. This equation doesn't seem right for this reason. And Drude wrote back and said, you should see my paper, and cited a paper. And Einstein wrote to his girlfriend, then wife, Mileva Maric, he said, authority has gone to his head. This is the enemy of science, roughly speaking. And I think he believed that he had a tremendous confidence in the possibility of reasoning correctly. And it wasn't that he thought these people were stupid. I never read anything like that from him about these senior physicists. But that he thought that they were rigid in their obeisance to authority. And that's what he hated. That's why he gave up his German passport. That's why that guided his sort of philosophy of life and his politics all his life, as well as his attitude towards science. In fact, sometimes in ways that didn't advance him very far. For instance, he would not take it on the authority of the senior quantum physicists that the theory was complete. He would not take it on the authority of people later in life, in elementary particle physics and elsewhere, that his search for a unified field theory in the way he was going about it was promising. And he was proud of his sort of stubborn independence. And that from a very young age. Yeah.
I think he felt he earned his independence early on. But what I was going to ask is there any indication now in what you've read that he was aware of the Morley experiment, or was he really looking at the concept because of Maxwell's equation?
There are two rounds of the Michelson-Morley experiment. In the first round, they were accurate to, roughly speaking, the ratio of the speed of orbit of the Earth around the Sun to the speed of light. So 1 in 30,000 or something like that? 1 part in 30,000. The second experiment was much more accurate. It was accurate to v squared over c squared, so 1 part in 30,000 squared. So for many physicists, the second later Michelson-Morley experiment, I think it was 1887, but I'm not sure, was the one that was crucial for them, because that's really what they thought nailed the problem of the ether and nailed that the null result clearly. Einstein certainly knew about the first result. And he always said, and there's no good reason to disbelieve him, that he just didn't know about the second. You see, Einstein, it's interesting that people often get something backwards about Einstein. And that is, in the contrast with Poincare. They say Poincare was a mathematician, and so he wasn't really understanding what was physical about the world. And that Einstein was a physicist, and he did. In an odd way, it's actually backwards. Poincare was trained also as an engineer. So when he said back in 1898 that it'll never be worthwhile to correct our instruments for the time of transit of the signal because other errors are bigger, it's because he knew. He knew how big the personal errors were of tapping. He knew all of the details of the technology. Einstein was in a different position. Einstein was in the patent office, often trying to make a decision about whether something could work in principle. Einstein didn't have to mill the works to get it right. And he didn't have to do the timing experiments. He had to understand the technology, but applying principles. Let me give you an example. Einstein's opinion about his patents were destroyed, like all patents in patent opinions, are destroyed 20 years after the fact. So in 1925, the Swiss, even though Einstein was the most famous physicist in the world, dutifully destroyed all these things. I could kill him. Anyway, but there were a few that survived, and the ones that survived are ones that were litigated. And if they became court records, they survived. So Einstein, there was a battle that went on between Elmer Sperry, who had stolen, essentially, a patent from a physicist in Germany named Einstein-Poincaré. And so it went to trial, and Einstein-Poincaré attacked Sperry, and Einstein was called in as an expert. So Einstein had to testify as to whether this was right. And the way you defend yourself in such a suit is you say, oh, I found this patent that's much older, and it had the same idea, so the guy that's accusing me didn't invent it. So that's what Sperry did, an old Foucault experiment, actually, a patent. And Einstein took a look at it and said, this is to make a compass out of a gyroscope. And he said, this gyroscope can only move in 2 dimensions. It has 1 degree of freedom too little. And so when the boat tips, it'll process like crazy and it'll go nuts. It won't work. It won't work in principle because of it has to rotate on 3 axes. And that's what Einstein-Poincaré did, and that's what Sperry stole. That's typical Einstein. You look at the patent, you extract all these complexities away, and you nail the principle. And that's, in a sense, the difference between these 2 guys, I think.
Let's take one more question.
Yeah.
Mine's more in the form of a comment. As a non-physicist, science-challenged individual, I want to thank you for your presentation and for
Thank
shutting
you.
off light bulbs.